Give me a bit. I just need to set this up. Oh, there you go. I'm live and running. Alright, so this is what you can see. Let me move that there. Move this that way. And okay, I'm heard. I'm heard pretty well. I just gotta copy the link. I'm just gonna send it before we start. Let me just write the physics away. Let me just send it to people. That should be that. There you go. Just send it. Alright. And then where can I find? I cannot. There you go. Okay. Okay, wait, I just need to get to check if my audio is fine, because I can't really tell. Okay, yeah. Okay, my audio is fine. I just need to remember where the camera is facing. Move the camera a bit. Alright. Okay, so I guess without further ado, I'm just gonna jump straight into it. So today, I will be teaching physics, specifically thermodynamics and electrical potential, electric charging, electric fields, and stuff like that. So we're just gonna go straight into thermodynamics. Thermodynamics. So let me write this down. Thermodynamics. Now, just from the term itself, thermodynamics. So thermo, as you could probably could tell, is relating to heat, and dynamics is relating to motion. So when you say thermodynamics, in a way, you could say that it is the motion of heat. Motion of heat. Or it can also be known as the transfer of thermal energy. So this is a field of physics that studies the transfer of thermal energy, or heat. So thermal energy can also be a fancy way of saying heat. So people who study thermodynamics study how particles move, how they interact with one another, based on the temperature. So for the most part, the hotter something is, the faster the particles move, as we learned in chemistry. So when it comes to thermodynamics, there are different kinds of heat transfers or exchanges of heat. So those three being conduction, conduction. So this is heat transfer between solids. So this is, as it states, heat transfer between solids. So it's just between two solids, not liquid, not gases. It's specifically for solids. Then convection, you have the second one. This is the transfer between fluid phases. So this refers to liquid and gas. Between liquid and gas. So that's what convection refers to. And then lastly, we have radiation. Now radiation is, as you may guess, a transfer of energy, or a way that particles transfer energy. But it doesn't need a medium. So it can transfer it in a vacuum. So these are the three different kinds of heat transfers. You have conduction between solids, you have convection between liquid and gas, and then you have radiation, which is in a vacuum. Okay, so those are your forms of heat transfer. So moving on, we're going to go straight into the first law of thermodynamics, which is also known as the law of conservation. Now, I don't know if I can just write all of this on the whiteboard. I will see how this looks like on my phone, if you can just read it, because I'm kind of lazy to write it all down. Basically, it states that the first law of thermodynamics, it says that energy, I actually don't know if you can see this, I'm so sorry. Energy cannot be created nor destroyed, but can only transform to another form. So, what it simply means is that it's pretty self-explanatory. Energy cannot be created or destroyed. It's impossible to form energy out of nothing. And it is also impossible to completely eradicate energy. It can only be transformed to another form. So for example, if you're to get energy from heat, you can turn it into mechanical energy, or you can also get it the other way around. Energy can only be dispersed and transferred. It cannot be created or destroyed. So, with that being said, we can move on to our first formula and set of equations. So this is the equation for change of internal energy. Now, internal energy is basically all the thermal energy, or sum of all kinetic energy within a system. It's inside the system. That's what internal energy is. It's actually represented by U. So internal energy. And then next we have Q. We're going to have our variable of Q, which is basically heat. Now this can be done, this could be added to the system, or it could leave the system, which will be a little important once I introduce the formula. And then lastly we have work, which is represented with a W. So the formula is this. The change of internal energy, which is represented by delta sign, then U, is equal to heat, Q, minus work. So this is the formula that we're given. It's very simple, right? However, there are some conditions, because this formula will be changed depending on the problem that's given, which is why I'll write this down. Now, Q is positive if work is done, if heat is added to the system. So if a problem were to give you, let's say, 75 joules, I think, or 75 Celsius, 75 Kelvin. Yeah, sorry, my fault. 75 Kelvin. Oh no, I am wrong. Joules, again. Sorry. 75 joules added to the system. That means the value of Q is going to be positive. However, if it is stated that 75 joules leaves the system, it is then negative. Because heat is being moved away from the system. It's being removed. Leaving. Now, the sign for the variable can also depend on the work, rather. So the statement and how the problem is given can also change the value of work. It's not just heat. So W is positive if work is done by. If work is done by the system. So W will be positive. However, W will be negative if work is done on the system, meaning that the environment is putting, or the environment is working on the system. It's adding work to it. If that makes any sense. If work is done on the system. So again, it could be positive or negative depending on the way the word problem gives it. Q is positive if heat is added or if the environment adds heat to it. Q is negative if heat is leaving or the thermal energy is being released from the system. Work is positive if it is done by the system, and work is negative, it is done on the system. So before I continue, I'll just explain what a system is because I just realized I didn't explain it. A thermal system is basically a set of items that generate thermal energy in a very simple way. That is what a thermal system, the system is, or engine system. So, with that being said, there are just a few terminologies that I would like to explain. So again, thermal energy or heat is basically energy of the system that is due to the movement of particles. So again, thermal or heat energy is the energy of the system that is done to the movement of particles. Okay. Next, we have the second law of thermodynamics. So the second law of thermodynamics basically tells us what processes can occur in nature and what can't. Now, there are two statements specifically. There is one by Clausius. I'm not going to state his exact words, but he's basically saying that heat flows spontaneously from a hot object to a cold object. So I'll just paraphrase it. Heat flows from hot to cold. So the thermal energy, or heat rather, can only flow from hot objects into a cold object. Cold objects will never flow spontaneously from a cold to a hot. That doesn't happen. So according to him, it's hot goes to cold, not cold goes to hot. Then there is a second statement, which is Kelvin Planck. I think it's a conjunction of two people. So he stated that no device whose sole effect is to transform given amount of heat completely into work can be created. So basically, no device can transform 100% of heat into work. So it's basically like a perpetual motion machine. Those things don't exist. It's impossible to completely convert 100% of heat into work. For the most part, it's actually impossible to convert 100% of anything. Okay, let me move the whiteboard here. I just realized it's not being seen. So that is what Kelvin Planck is. These are the two statements that is important to know. Again, I just paraphrased it. So again, Clausius said heat flows from hot objects to cold objects, while Kelvin Planck said that no device can transform 100% of heat into work. It's that simple. It's impossible to create a 100% efficient engine. So, these engines, or heat engines, are basically devices that converts thermal heat into mechanical energy. Thermal energy into mechanical energy. A good example of this would be steam engines. How steam engines work is that it's basically boiling water. So you add fire, usually coal, to a giant fireplace. It boils the water turns into steam, hence the steam engine, and all that thermal energy turns into mechanical energy, which is why they're very common in trains. And it would convert the mechanical energy to make the train move. So that is an example of a heat engine. Now, when it comes to heat engines, we can actually determine its efficiency. So there are two formulas for this. So the first one being EFF. This stands for efficiency. It's just a shortened, it's like an abbreviation, abbreviated format. We have this QC, which is basically heat dumped to cold reservoir, or heat added to cold reservoir. And then we have QH, which is heat input from hot reservoir. From hot reservoir. Okay, so these are what the variables mean. So you're going to have EFF, which is efficiency, QC, and then QH. Now, QH, it's important to note that it is almost always the hotter given. So if you're given a word problem for this, it is almost always the hotter one. So in this case, if I'm not mistaken, the unit that would be given for this, I believe, would be kilojoules. The unit for this would be kilojoules. So whatever has the higher amount of kilojoules will be in the denominator. I just realized I didn't give the formula. So there's the formula. So efficiency equals 1 minus QC over QH. So this is all in kilojoules. So for example, let's have a problem. Let's say you were given this. Find the efficiency of this heat engine if the heat added to the cold reservoir was 1,500 kilojoules. So automatically we can say that this is our QC, and then the heat being added from the hot reservoir is 2,000 kilojoules. So that is going to be our QH, because it's automatically the hotter given with a higher kilojoule input. So now that we have this, we're looking for efficiency. We don't know what efficiency equals to. So we're just going to use the equation. Efficiency equals 1 minus, we're just going to plug in the values already, 1,500 kilojoules divided by 2,000 kilojoules. So we're simply just going to divide this. This is going to equal to 1 minus 0.75, or 3/4. And then it's going to end up being 0.25. Now you can convert this into percentage, and it'll be 25%. Meaning the efficiency of the heat engine that we just calculated is 25%. So again, you have the colder one, which is QC, and then you have the hotter one, which is QH, and then just input it, substitute the values, and that is how you get the efficiency. Pretty straightforward. There's another one that is given. So what if you aren't given kilojoules? What if you were given Celsius or Fahrenheit? So that's where this formula comes into. So it still is going to be the same. We're still looking for efficiency, but it's going to equal to T hot minus T cold over T hot. So this is just going to be similar to the QC over QH. As you can see, we're still doing division. However, we're given Celsius. We're given degrees of the temperature. So if we're given Kelvin, we're just going to input it. Judging from the words already, the T sub hot automatically means that it's the hotter temperature. And then T sub cold means that it is the lower temperature. So for example, let's say we're given, I don't have a word problem for this, so I'm just gonna put the given here. Let's say our T hot is equal to 100 Kelvin. And then our T cold is equal to 10 Kelvin. So we're simply just going to try to find efficiency. We're going to input it with the formula. So that would be 100 Kelvin minus 10 Kelvin divided by 100 Kelvin. So 100 minus 10 is going to equal to 90. 90 divided by 100 is basically 0.9. So this is going to be 0.9. Then the unit cancels. So you can convert this immediately into you can convert it into percentage, and it'll state that the efficiency of this engine is 90%. Just like that. Very simple. So, since we've covered the efficiencies of heat engines, we can move on to another formula. So don't worry, all of these formulas are actually pretty straightforward, thankfully. There's nothing too long. Our next topic, or our next term, is entropy. Now, entropy, in its most simple terms, is the amount of disorder within a system. Just how chaotic it is, how messy. So if messiness had a unit or a way to measure it, it would be entropy. Now, there's actually a way to find entropy using an equation. So that would be the change of this. I don't know why I didn't put down the symbol, but it's delta S equals Q over T. Now Q is heat transfer. Heat transfer. Oh, this is a change in the system, I think, if I'm not mistaken. That's what S stands for. Correct me if I'm wrong though. This is measured in joules. And then we have the T, which is temperature, which is measured in Kelvin. Just like that. So this is the formula for entropy. It's very straightforward. You really just have one term at the top and one term at the bottom. And this is how you measure or find the entropy of a system. And the unit of this, the SI unit, is just joules over Kelvin. This is the SI unit. Okay? So it's just like that. Very simple for entropy. Now, there are processes that can occur within a system. They could be reversible or irreversible. And I think that's pretty self-explanatory. Reversible processes basically mean these are processes that can be reverted. They can be turned back into their original state. So it's similar to crushing a bottle and then blowing air back into it. The bottle will regain its shape. Or a better example yet is a balloon. If you fill up a balloon with air and then deflate it, you can fill up the balloon again with air. That's a reversible process. However, an irreversible process is basically one where you can't revert it back to its original state. So it would be like tearing a paper. If you were to tear a piece of paper, it would be really hard to put it back exactly the way it was before. So that could be an example of an irreversible process. Or burning something. You could burn a paper or you could burn a house. It's going to be really hard to get them back into their original state. So those are the types of processes. Now, we're going to go back to laws of thermodynamics. This is going to be purely terminology. And I don't think I can write all of this, but I'll just send my screenshots of my notes if you guys need. So, firstly, we have the zeroth law, which talks about equilibrium, thermal equilibrium. It states that two systems in an equilibrium with a third system are in thermal equilibrium with each other. So basically, for example, if there are two systems, let's say we have one system here, another system here, and the third one here, if they are in equal levels of thermal energy, basically, if they are in equilibrium with this third one, let me just label 1, 2, 3. If they're in thermal equilibrium with the third object, that means that all of them are actually in equilibrium. So one is in equal terms with the second system, the second system is in equal terms with the third one, and the third one is in equal terms with the first one. That's what the zeroth law talks about. Zeroth law. Second, first, we have the first law, which is the one I stated earlier, the conservation of energy. Again, it states that energy can change forms, but is neither created nor destroyed. Second is about entropy. Now, it is a little confusing that we have two second laws of thermodynamics. So, I would just like to clarify that I think it is best to just keep both of them in mind. So, the second law of thermodynamics can state that there are processes that can occur in nature and what can't. But in this case, there's another second law for some reason. This is just about the entropy of an isolated system. It always increases for some reason. So a system that is alone, so this is the only system. We're going to get rid of the first and second and third one. If there's a system that is completely isolated, basically completely alone, its entropy will always increase. The change in S will always increase. Now the third law is also about entropy. It states that the entropy of a system approaches a constant as temperature approaches absolute zero. So once the temperature reaches absolute zero, which I believe is 0 Kelvin, or well, looks like OK, but once the temperature reaches this, the entropy of a system starts to stabilize. It starts to reach a constant value. So now that we've discussed these, there are some things we just need to refresh ourselves with. One of that being Boyle's law. So I'm sure you're familiar with Boyle's law. This this shows the relationship that pressure has with volume, well, with gases, right? So the formula being P sub 1 times V sub 1 equals P sub 2 times V sub 2. Again, you can only use Boyle's law if temperature is at a constant. So you can manipulate it with however you want. If you're trying to find V sub 2, you just divide both sides by P sub 2. So in that case, you'll just be given this. It's like that. So just a throwback, just so you can refresh yourselves, because we might need to use it. Okay. So the next few are just going to be terminologies. I won't be having word problem solving for a while. So we have here a thermodynamic system. So as I stated earlier, this is just a collection of objects or things that exchange energy with its surroundings. So basically they just have constant transferring of energy with one another. Thermodynamic process, these are the processes or the transferring or the exchange that happens within a thermodynamic system. Now that we know about these thermodynamic processes, we can actually talk about the different types. Now, the different types of thermodynamic processes depends on what's constant. So, if we were to have a constant pressure, we're going to have an isobaric process. So again, this is when it's at a constant pressure, which I'll label with as a capital P. So this is constant. This is an isobaric process. It's a change in volume, basically. Isobaric, change in volume. Change in volume. Second, we have isochoric. Now, if pressure was constant, this time volume is what's constant. So we're going to put constant V. And then, yes, you guessed it, it's a change in pressure. Thirdly, we have isothermal, and as you could guess, it is a constant temperature. Isothermal, constant T. So this is a process, any process with constant temperature. So it could change pressure, it could change the volume, it could change both. As long as temperature is constant, you can tell that it is an isothermal process. And then lastly, we have adiabatic. So this happens when there is no heat exchange. So basically there is no transfer, there is no exchange, there's no trade. That is what adiabatic means. So again, these are the four different types of thermodynamic processes. We have isobaric, constant pressure. We have isochoric, constant volume. Isothermal, constant temperature. And lastly, we have adiabatic, where no heat is exchanged. I will just drink some water because my throat is getting a little dry. Okay, we are officially done with thermodynamics. Pretty quick. So let's move on to our next topic, which is electricity and magnetism. So I'm sure that all of you know that the most basic unit of matter is an atom. Now, atoms have parts of them. An atom isn't just one thing. An atom is composed of three things. You have the electron, you have the proton, and you have the neutron. Now, these parts of the atom can have charges. The electron has a negative charge, the proton has a positive charge, and the neutron is completely neutral, hence the word neutron. So, considering that the electrons and protons have charges, you can say that in some sense, everyone or everything has some form of an electric charge. So, when an object specifically interacts with another one or has an imbalance in the electrons and protons, it is specifically electrically charged. So for example, if this marker were to have one extra electron than it has protons, then it is technically electrically charged. Now, you can tell what kind of charge it is, if it's negatively charged or positively charged. Well, since an electron is negatively charged, if an atom has more electrons, it's negatively charged. If an atom has more protons, it is positively charged. So again, the positive particles are protons, and then the negative particles are electrons. So these determine the charges of an object. Now, similar to the law of conservation, charges cannot be created or destroyed. And electric forces, which are the forces of electricity or charges, can attract or repel. It's like magnets. North attracts south, but it repels to north. So you can't have two of the same charges. You can only have opposites. Now, charges are measured in coulomb. So first, usually in equations, charges are usually represented by this, a Q. Now for its SI unit, it is written in coulomb, which is spelled like this, or represented with a capital C. Now that we know this, let's take a look at some values for the protons. And this is where the weird looking figures start to come in. So scientific notation, because we're dealing with subatomic particles. So protons, I'll label the mass here, or I will move it a little bit more in the middle. So we're gonna have the mass here, and then we're gonna have the charge. Now the mass of a proton is measured at specifically kilograms here, 1.67 times 10 to the power of negative 27 kilograms. Well, the charge is positive since it's a proton, so it is positive E for some reason. 1.6 times 10 raised to negative 19. Okay. And then for the electron, on the other hand, its mass is actually even smaller. It's at 9.11 times 10 raised to negative 31. And since it's an electron, it's negative. So negative E equals the same charge, except it's just negative. Times 10 raised to negative 19. So these are the default values if not given by the word problem. So if you aren't given the values of a proton or an electron, these are what you can consider. Yes, it is a little bit much to memorize, but unfortunately, that's how physics works. Sometimes you have to memorize it. Okay, so now that we know these values, I will explain to you the methods of electric charging. Now, when it comes to electric charging, there are different ways, different mediums, different methods. One of them being charging by friction. Simply put, you're rubbing two objects against each other, and that will generate electricity. So usually the more friction there is, the more energy that could be charged. That's why sometimes you might experience a little bit of static electricity when you touch something metal. There's an imbalance that was usually caused by friction. Secondly, we have charging by conduction. This is when a neutral object is placed with an already charged object. So think of it as like a neutral object is basically an object that has no imbalance. And if you put it with an object that already has an imbalance, that's already being charged, it's going to be charged because of the object that has an imbalance, which is the charging by conduction. And thirdly, we have the charging by induction. This is basically a form of charging that has no contact. There's no physical contact. There's no direct contact. It's why you have something called an induction stove. It uses this principle to cook your food. Now, there is something called Coulomb's law, which basically states that it can give the electric force between 2 point charges. So it just gives you the electric force in between two specific points of charged things. Now, another thing to take note is that there is something called an electrostatic force. Now, an electrostatic force basically refers to the attractive or repulsive force between charged objects. So it's the type of force that pushes magnets away or pushes them together, the attraction and repelling. So it states that electrostatic force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Now, here's something that I want you guys to take note. This is more of a math thing than it is a science thing. But when you hear the term proportional, right? Let's say if electrostatic force is directly proportional to the product of the charges, it means electrostatic force will go up if the product goes up. But another way you can see proportional is actually just multiplication. And then if you're going to see inversely proportional, it is simply just talking about division. Now, it might not make a lot of sense, but once I show you the formula, it makes, well, greater sense. So here, we have here our F, which is electrostatic force. It is equal to K. This is Coulomb's constant, which I will show later, times Q sub 1 times q sub 2 all over r squared. So remember earlier, I stated, or the lesson stated, that electrostatic force is directly proportional to the product, basically when two terms multiply, of the charges of the charges. So here, these are our charges, q sub 1 and q sub 2. Again, charge is represented by the letter q. So notice how they're being multiplied together. It's proportional to this. But electrostatic force is inversely proportional to the square of the distance. The square of the distance. This is your distance, r. Now it's inversely proportional because it's at the denominator, meaning you're dividing with the distance. Hence why it is inversely proportional. So just keep that in mind. If something is proportional, you're multiplying it with the thing. If it's inversely proportional, you're dividing it. So now that we have this, I'll just break it down. This is expressed in newtons, the electrostatic force. This is Coulomb's constant. Coulomb's constant, meaning it never changes. It's like how gravity always has a constant value, or c, which is light. So this is equal to 8.99 times 10 raised to positive 9 Newton meter squared divided by c squared. So this is Coulomb's constant, if you can see it. Yes, it is pretty long, but that is the constant that Mr. Coulomb decided to create. 8.99 times 10 raised to the power of 9 Newton meter squared divided by c squared. So now that we're given this, there are also some other units to just keep note of. So sometimes in word problems, you'll be given two different types of Coulomb. So you're going to be given NC, and you'll be given mu C. Now, I don't really know how to make mu that well, so you have to deal with this. So this stands for nano Coulomb. Nano Coulomb. Okay, this marker is already starting to die. I hope you can see it. You can kind of see it. Okay, so nano Coulomb is basically equal to the value times 10 raised to negative 9. It's just raised to negative 9. However, this mu one is just micro Coulomb, so it's not as small. This is just times 10 raised to negative 6. So it's not as small as a nano Coulomb, so just keep that in mind. Nano is always smaller than micro. Okay, so let's have an example problem of this. So an example problem of this would be, I'm just going to list the givens. And I'm going to trust that my notebook is right, because I don't have my calculator with me. I left it upstairs. Okay, so let's say that we were given this. Our q sub 1, which is our first charge, is equal to negative 6.25 nano Coulomb, which we will convert to 6.25 times 10 raised to negative 9 Coulomb. And let's say our q sub 2 is also the exact same. Negative 6.25 nano Coulomb, which again will be converted into 6.25 times 10 raised to negative 9 Coulomb. We have our r, which is the distance that it was given, 61.7 centimeters, but we're going to convert it into meters, so it's going to be 0.61 0.617, or simply 0.62 meters. And then we have Coulomb's constant, which is equal to 8.99 times 10 raised to 9 Newton meters squared divided by c squared. So this is our given. Now we're looking for electrostatic force. So we're simply just going to plug it in the equation that was written earlier, which is F equals K times Q sub 1 times Q sub 2 all over R squared. However, it can also be written like this. F equals K Q sub 1 times Q sub 2 all over R squared. So you can do it like this as well. You can treat it like that. So let's try this out. Okay. So we're gonna plug in the values. I will be using this one at the top, so it's quicker. So we're gonna have F, oh boy, F equals Coulomb's constant 8.99 times 10 raised to 9 Newton meter squared divided by c squared times negative 6.25 times 10 raised to negative 9 coulombs times the same thing again. It's 0.25 times 10 raised to negative 9 coulombs. So this is the substitution. Oh wait. All over 0.62 meters squared. So if you multiply these parts first, if I'm not mistaken, you should be given this. Okay, wait. Let me just copy down Coulomb's constant. It will then be 3.91 times 10 raised to negative 17 Coulomb squared. So this is probably what it results to. Again, I don't have my calculator with me, but I'm just trusting my notebook. And then the denominator will end up being 0.38 meters squared. Now, we can actually cancel some units. You can see that the c squared here is being divided with Newton meters squared. So you can cancel out the c squared. And then you can see that the meter squared is in the denominator, while the meter squared here is at the numerator. So you can cancel it out. Now when you cancel that out, you're left with 8.99 times 10 raised to 9 newtons divided by 0.38, which will then equal to 2.1 times 10 raised to negative 6 newtons. And that is your answer for electrostatic force. A lot of writing, but it is actually really simple. It's just division and a bit of multiplication. So that is how you get the electrostatic force. Pretty simple. But what about electric fields? Before I move on to that formula, what is an electric field? It is basically, a field of electricity, if you're going to really just take a look at it at its value. So specifically, it is an invisible area of influence surrounding an electric charge or group of charges. So almost all charged particles or charged objects emit an electric field. So if you're going to find the power of it, we would be using this formula, which is E equals K Q over R squared. So again, we have the same things, Coulomb's constant, the charge, and the distance. Now, there are different ways you can approach this, but if I'm not mistaken, you could combine the K with the Q, but if you don't want to, that's fine. Because I think I made a mistake during a quiz and I got traumatized for it, so I'm just going to do this part first and then multiply it. So, for example, if I were given this, E equals, So if, for example, we were given these, so let's say our R is equal to 1 meter, and then our Q is equal to 5.6 new coulomb, which is basically 5.6 times 10 raised to negative 6 coulomb. Our K being the same as usual, 8.99 times 10 raised to 9 Newton meter squared over coulomb squared. So we have lesser variables to work with since there's lesser that's required. We're just looking for one particle, not two. So we're just going to substitute the values. So you can write it like this, 8.99 times 10 raised to 9 Newton meter squared over coulomb squared times the charge, 5.6 times 10 raised to negative 6 coulomb, all over 1 meter squared. So this is how it would be looking like. And this is what E would equal to. And then you're simply just going to divide this, which is actually going to be pretty straightforward. You can actually even cancel it out. Oh, my dog. You can actually even cancel it out, right? Because you have a C here and a C there, and then a meter here and a meter squared there. So you could multiply it with this already, or you can let this do its division first. It's up to you. But let's say this is going to do its division first. Let's just say for that case. So it will just simply be 8.99 times 10 raised to 9 Newton meter squared. I'm sorry if you can't see it, but I'll just be explaining it. So Newton meters squared divided by coulomb squared times the result of dividing it, which is still going to be 5.6 times 10 raised to negative 6 coulomb over meter squared. Because there's a meter squared at the bottom. Now you can simply just cross it out. There's one C here at the numerator and one C and two of them at the denominator. 2 meters here at the denominator and 2 meters at the top. So you'll be left with supposedly this answer. 5.03 times 10 raised to 4 newtons per coulomb. So this is the final unit, newtons per coulomb. And this is your E, your electric field. So that is your answer. Oh, and also, just a note, the charge of your answer determines the direction of the electric field. If it's positive, the answer is repels. It repels things away. Because when it comes to electrical fields, positive charges, positive objects or protons, they repel things. So they're pushing things away. But if it's negatively charged, it's attracting things. It's pushing things towards it. It's pulling things towards it, rather. So if it's positive, it's repelling. If it's negative, it's attracting. Okay? It's just that simple. Now lastly, we just have a few rules, a few notes, and then one more formula. And that will literally be it for this quarter. So I will just talk about the notes, and then we'll move on to the formula. So potential difference refers to the difference in electric potential between two specific points. The SI unit of potential difference is, I'm already getting confused. The SI unit of current is A, or amperes. It's actually unrelated to the potential difference for some reason. I don't know why I included it here. But I just think it's something you should know. And I actually don't know if I should cover this because I don't know if this is really related. I'll just send pictures of this. I'll show this on stream. I don't know if you can actually even see it. My stream preview is not loading on my laptop. But let's see. Anyways, okay. So since those are just the notes I need to cover, we have one more formula to talk about, which is electric potential. Oh, there you go. I just came from talking about it. So electric potential, again, electric potential determines how much work is needed to move a charge. So electric potential can be measured or found by using a formula like this. Oh no, I hope you can see this. V equals W over Q, or V can equal K capital Q, which I think is actually just still normal Q, over R. Now, V is the electric potential, W is work, this is work, specifically in joules. So, like usual, it's measured in joules, and then Q, which is the charge, is measured in coulombs. Oh, I should specify charge, but it's fine. Now this, I don't know why I didn't write anything for it, but this is Coulomb's constant. I assume this is also just the charge, and then the R is just the distance. So we have a formula. I'll do an example problem. But it's not going to be the usual problem. It's actually going to be the transposed, the derived one. So let's say our given is V. We already have V. So we have 150 V, we have 150 V. What unit is this? I think it's Newton? Joules per coulomb. That's Newton. Hold on, sorry. Is that Newton or is that volt? Sorry, it's volt. My ineligibility. Sorry. 1 volt. 150 volts. Sorry. So, or 150 joules per coulomb. I'll just put J over C. And then we also have our Q, which is 2 coulombs. Now we need to find our W, the work, since it's the one that's missing. So it's actually pretty simple. If our formula is V equals W over Q, we're simply just going to transpose it. We're going to derive it. Since we're looking for W, we're going to multiply the entire equation by Q. So the denominator gets canceled, and you're going to be left with V times Q equals W. So you're going to substitute it. So 150 volts, or joules over coulomb, times 2 coulomb. You're going to cancel out the units, and you'll be given 300 joules. And that is the electric potential, and that's how you find it. So again, that covers everything there is to learn in general physics, 3rd quarter. Wow. So that covers thermodynamics and electric fields, electric potential, and all that. So I believe it is really important to memorize the formulas because I'm not sure if we're going to be given an index card. So please memorize the formulas if you can. It's not the most complicated. I will try to post a picture where it's all condensed into just one page or something, which are just all the formulas you'll need to know. Or at least all the formulas I was able to take note of. I could be missing some, but yeah. That is everything you need to know in general physics, and I hope you learned something, and thank you for watching. And I'll see you in the next one.